Well, there isn't now. That's I feel bad about that. Sorry about that. Sorry for the people at home. Oh yeah, okay, well, I guess at this point it might, I should still. Yeah, wow. Sorry, I got so into the math, I forgot about the zooming. Sorry, let me do a couple things here real quick. Apologies. I'm so excited to do things. There we go. Thing. Come on. All right. Let's see here. So trying to estimate this, right? So we're going to say, well, I need to bound the error, right? I want this to be accurate to 2 decimal places, meaning, what does that mean really when we say we want something to be accurate to 2 decimal places? Like so that means let's just see what e to the -1 actually is, just for reference here. Let's see, where's e? Sure. It's about 0.367. So basically, we're trying to say, well, we want these 2 to be right. We don't care about the third one. So how far off could we be from this and still have the first 2 decimal places be accurate? It's a good question. I feel like the answer is usually kind of half the next decimal place. Like we could be as off by as much as we want the error to be less than or equal to 0.005. But that might even be too much. I don't actually know. This is all, I will freely admit, this is the kind of question that's always kind of been challenging me for wrap my mind around. Like, why do we need it to be this way, not some other way? And yeah. So let's see here. So we're going to estimate the error. We're trying to estimate e to the -1. Our center is 0. Our x is -1. Our z has to live between there. So again, not very exciting. If our z is between 0 and -1, and we know we're trying to find a maximum for the n+1 derivative of our function, it's still going to be the same 1 that we had last time, right? Because our error, whatever it is, is going to be less than or equal to, well, the n+1 derivative at z. If z is between -1 and 0, that's just going to be 1. X minus c, well, x is -1, c is 0, so I'm just getting a -1 to the n+1. That's not going to really affect the value at all. And then the only thing that's actually going to matter is n+1 factorial. So really, this just boils down to being equal to, or less than or equal to 1 over n+1 factorial. And so what I'm saying here is, I think, and again, this is really I think what we're going to find out, that we need 1 over n+1 factorial to be less than or equal to 0.005, which is 5 over 1,000. Let's see. So, which is 1 over 200, I guess, if you like. I know that n equals 3 isn't big enough, because n equals 3 would give me 1 over 4 factorial. I know that n equals 1 over 24, not small enough. N equals 4 would be 1 over 5 factorial, which is 1 over 120, still not small enough. But n equals 5 would give me 1 over 6 factorial, which is 1 over 720, which is small enough. It's less than this 1 over 200. Now, again, I will freely admit, I feel a little shaky about this. I'm not really 100% sure that this is the right thing to say to be right, to be correct to 2 decimal places. But I think I'm really not sure. Sometimes you're just not sure about things. Okay. I feel like I'm going to go look at this later and get you a better answer before Friday. So yeah, I will do that. Let me write myself a note here. Now, the bigger picture here is that even though this stuff is not like this stuff certainly matters a little bit, but I don't imagine this is going to be the majority of your exam. So I'm certainly happy to address other questions about this. If you have other questions, it's probably not a bad idea to think about those as well. His tests looked relatively, they looked hard, but not unreasonable. I certainly would imagine he might ask some sort of question about showing something converges using the monotonic convergence theorem. That seems like something he's likely to ask. Sure. So there is one in the practice exam I gave you. I don't want to do that one because I already know the answer to it, and I would like to give you the opportunity to do it on your own. So let's say we had something like, so we have to make stuff up. Oh, sure, we can just do that. Let's say we had something like where an plus 1 is equal to the square root of 6 times a sub n. And a sub 1 is equal to, let's make it fun, a sub 1 is equal to 1. Okay, so we want to show, actually we want to determine, because maybe this doesn't converge. Maybe I made up something that actually doesn't converge. We want to show this converges if it converges or diverges if it diverges. So here's what I would always recommend doing if you have a problem like this. Figure out what the limit could be. So even if that's not the first thing they ask you to do, like maybe they're going to ask you to show it converges first, but it's nice to know what the limit's going to be because that helps you figure out how to do the rest of it. So 1, find the potential limit. The reason I say potential is because the number or numbers, plural, that we find here might not actually be the limit. Especially if there's more than one of them, for sure, only one of them can be the limit. So here, we're going to set both an plus 1 and an to be the limit L. So we're going to solve L equal to the square root of 6 times L. And this one has a pretty straightforward solution. Square both sides, get L squared equal to 6L. Subtract 6L from both sides. Factor. And you get either L equal to 0 or L equal to 6. Those are the 2 potential limits. So the idea here is, and this is a common tactic, is what we're saying is, if the limit exists, then we know that the limit as n goes to infinity of a sub n has to be L, but also the limit as n goes to infinity of a sub n plus 1 has to be L. So the idea is basically we're just taking the limit of both sides. The limit of a sub n plus 1 is L. The limit of the square root of 6 times a sub n is going to be the square root of 6 times the limit of a sub n, which is the square root of 6 times L. So this is essentially what we get by, we're just letting n go to infinity. And saying, okay, well, that's going to go to L, and that's going to go to L, and that's going to go to L. So our potential limit is, well, it's not 0. And the reason we know it's not 0 is because, well, we can see that if you start plugging in values, if we're starting at 1, start plugging in values for a sub n, we're going to get larger and larger values, which we'll actually use in a minute to show it's increasing. I will also point out, if our first term had been 0, then the limit would be 0, because you would plug in 0 and you would get 0 back, and you plug in 0 and you get 0 back. So you might actually start in the place where the other thing is the limit. Probably not on your exam. So then I need to show two things. I need to show bounded and monotonic. I would usually go for bounded first. Here's why. Often the limit you have found is going to be your bound. So here's what I'm going to say. One, I know that a sub 1 is less than 6. It's given. 6 is probably the bound. You can pick a higher number, but you actually using the actual limit is usually the easiest way to do it. And then thing two, I want to show that a sub n plus 1 is less than, sorry, not less, yeah, no, sorry, I'm doing this wrong, apologies. I was starting to do it, increasing, apologies. I want to show that the whole thing is less than or equal to 6. So I want to show that square root of 6 times a sub n is less than 6. Well, I know that if a sub n is less than 6, I know I'm starting off with what I kind of want, but that's okay. Then the next term, a sub n plus 1, which is equal to the square root of 6 times a sub n, is less than the square root of 6 times 6, which is equal to 6. I don't know if he's talked about this in class, but this is essentially what's called, oh my gosh, words. An inductive argument, where you say, if it's true for the first term and saying it's true for this term makes it true for the next term, that's enough, because we're saying, okay, well, a sub 1 is less than 6. And then if a sub 1 is less than 6, then a sub 2 is less than 6. And if a sub 2 is less than 6, then a sub 3 is less than 6, and so on and so on and so on. So this is a pretty normal way of showing something like this, especially for a recursive sequence. Basically, we say, I'm going to assume it's true for a sub n, and then show it's true for the next term a sub n. Yeah. I suppose you could work backwards and say, I'm going to say, well, I need this to be less than 6, and then work back to the fact that the previous term is less. But this is the way I would do it. And I think it's the way he kind of did it in his solutions for the first one, but now I'm not so sure. I would like to look and see. I'm kind of curious what he said there. All right, one sec. And the limit. Yeah. Yeah, he does the exact same thing in his solutions. He says that if a sub n is less than or equal to 2 in his problem, then I can show that the next one is also less than 2. So that's the way I would definitely recommend doing it if you see a problem like this. What else do we have to show? Yeah, monotonic, either increase or decrease. Now, I'm pretty sure that it's going to be increasing because I'm starting at 1, and I think the limit is 6. So I'm going to try and show it's increasing. So how to show it's increasing. That is, I want to show, then I will point out, for a non-recursive sequence or something that doesn't have a factorial, if you're trying to just show it's increasing or decreasing, the way you want to do that usually is by taking the derivative, if you can, and just saying it's either positive or increasing or negative. But that's not going to be an option typically in this kind of thing. So show it's increasing, we want to show that the next term is bigger than the previous term. That's what we're trying to show. So this is where we're going to use the recursiveness. Where we're like, well, I know that a n plus 1 is equal to the square root of 6 times a sub n. So the question here really is, I want to show that the square root of 6 times a sub n is bigger than a sub n. Well, is that true? Not always. It's actually not always true. Is it true when it matters for us? Well, let's see. So if that's going to be larger than that, then I need to show that the insides are bigger than that thing squared. Okay. Well, let's bring everything to the left, and I want to say that that minus that is bigger than 0. So I want to show that an times 6 minus an is bigger than 0. And that's true if AN is between 0 and 6. Right, which we already and which is why I will point out that we do I like to do the bounded part first, because I say, oh wait, we already know that AN is between 0 and 6. It's not the only way to do this part, but I think it's the way that's maybe the most straightforward. So that's what I would say. Yeah. Okay. The last thing or things I will say, I guess, well, I suppose, so then usually they want you to say what the limit is. I would say the limit was 6 unless they wanted me to show more, but I feel like at this point we've shown it's increasing, we've shown it's bounded. That means we know it converges. And if it converges, it has to converge to one of the potential limits. We know it's not 0, it's got to be 6. The other thing I want to say is just very quickly, do I have enough time? Yeah. As far as testing for convergence or divergence of a series, I want to remind you of just a couple things. Thing 1, remember the test for divergence. Or the nth term test, if you prefer to call it that. It's a really good way to show that something like this diverges. If you take the limit of that sequence, it's going to be not 0. Similarly, this sequence or this series, sure. 1 minus 5 over n to the nth power. That also diverges in the same sort of way. You can show that the limit of that sequence is not 0. Thing 2, if we see n factorial or some number or something raised to the nth power or both, ratio test. And the last kind of word of advice I have is, it was in my brain a second ago. Where did you go? Oh, I know what it was. It was God. Oh yeah. If you have a series where you have powers of n over powers of n, limit comparison with just the highest power on top over the highest on the bottom. So in this case, I would limit compare this to the sum of, let's see, the highest power on the top is n to the 6th. The highest power on the bottom is n to the 8th. So I would limit compare this to 1 over n squared, which would mean I am searching for convergence. Very, very specifically, if you have powers of n over powers of n, don't do anything else. Use limit comparison. That is definitely the easiest, fastest way to do it. Even if you could find a direct comparison, limit comparison is going to work faster. All right, that's all I have to say. I will point out again, that's all I have to say, but let me say more. The review that I handed out to everybody has solutions already posted on Canvas. The practice midterm that I made up that has like 4 or 5-ish questions in the same vein as Casal's, I will post solutions to sometime tomorrow so that you can definitely, and I will make an announcement or something so that you can look at them. But I do encourage you to take it as a practice test, see how it goes, and then I will put the solutions up there.
With 3, you can just do the P series.
Well, yeah, so I'm saying I'm gonna compare this, and I know this is convergent because it's convergent P series. So then I use limit comparison test with this against that to show that this converges.
a number means and then
Correct, yeah, exactly. Yeah,
I did them. Or like, I mean, practicing the term. So
Sure.
for that one, I did the ratio test. Does it
Wh-
work like
which one?
that? For one?
that looks like the root test, not the ratio
Oh,
test.
I mean, root test. Like, could I just do the 1/n on the top? Cause then it's everything up to the 0. If you plug in infinity, it'd be 1 on top, so it'd be 1/12.
That might work, but I feel like it's a little dicey here because cosine of something like that is fluctuating between values, so.
Well, like the parentheses would be all over the whole thing. So then
Right,
we-
I mean, it's not necessarily one, but I feel like the easier way to do that one is to actually just use absolute convergence. Because we can say that the absolute value, well, absolute and direct comparison, because the absolute value of cosine is always less than or equal to 1.
I think they said absolute convergence, but I don't
Right.
really know what that was again.
Because, well, the thing is, right, if you can show that the sum of the absolute value of the series converges, then that shows that the series is converging itself. And the reason we might specifically use an absolute value there is because if the absolute value of cosine, we can say that the absolute value of cosine is less than or equal to 1. And then it becomes easier to deal with.
And then this one, did they only look at n to the 5? So did they distribute the square root to like all of the terms?
Well, we can't really distribute the square root to all the terms, but what they're doing is we're saying that if we kind of ignore those last two terms. Right, if I said, I'm gonna look at the biggest thing. And so I'm gonna look at 1 over the square root of just n to the 5th, which is 1 over n to the 5/2. And then, I'm gonna use limit comparison to compare that, and that's gonna show
Alright, so
convergence.
that's all I would need to.
Mhm. But yeah, so typically when you have something like that, we kind of just ignore the lesser powers.
For this one, would you do the root test?
I probably would, that's where I would start anyway. I might try the ratio test, I might try the root test.
And then since this is a negative one, is it alternate?
It is alternating. I can't believe I forgot to start the Zoom, oh well.